All right, let's talk about the secret language that's running pretty much everything in our modern world. It's not programming code, not exactly, and it's not just circuits. It's the language of mathematical modeling. And it all starts by asking questions that sound, well, kind of impossible. I mean, seriously, think about this. How in the world do you teach a robot to do something that's super hard even for us? To balance a stick, not hanging downward stable, but straight up in the air. Where do you even begin to write those instructions? Or hey, let's zoom out, way out. How do you tell a satellite, whipping around the Earth at thousands of miles per hour, to aim itself perfectly at a tiny dot millions of miles away? There's no joystick, no do-overs. It has to be perfect. So how do we solve these insane challenges? Well, it turns out control isn't some kind of magic trick. It all comes down to one core idea: prediction. If you want to control something, you first have to be able to predict what it's going to do. And to do that, you have to understand it. And that's where this secret language comes in. Engineers create a blueprint of the system they're trying to control. But this blueprint isn't made of lines on paper. It's made of equations. It's a mathematical model that captures the physics of the pendulum or the satellite, letting them see the future in a way. This whole process, creating these special blueprints for systems that move and change, is what we call mathematical modeling. And believe me, it is the absolute bedrock of all modern control theory. So, what is a mathematical model, really? At its heart, it's just a set of equations that tries to describe how a system works. But here's the most important part. It's a simplified representation. It's never perfect. Think of it like a map. A map isn't the city itself, right? It leaves out a ton of detail, but it's incredibly useful for getting where you need to go. Same idea. And hey, don't just take my word for it. The source material for this whole explainer says it flat out. Getting the model right, making a good map, is the single most important part of the entire job. A bad model means you're lost before you even start. This brings up the biggest challenge for any control engineer. It's this constant tug of war between simplicity and accuracy. On the one hand, a simple model is quick and easy. It gives you a gut feeling for how things should work. On the other hand, a super accurate model is much harder to build, but it captures all those little real-world details. Finding that perfect sweet spot between the two, that's the real art. So, okay, how do we actually build one of these models? For a long time, the go-to method was what's called the black box approach. This was the classical way, the foundation of control for decades. And the name is perfect, because the idea is actually beautiful in its simplicity. We decide we don't really care what's going on inside the system. The gears, the wires, the physics, we just treat it like a sealed black box. All we want to figure out is, if we put this signal in, what signal comes out? That's it. Input, output. The main tool for this is something called the transfer function. Now that definition might look a little scary with Laplace transform in there, but don't worry about the math. Just think of it as a super clever mathematical trick that turns complicated calculus problems into simple algebra. At the end of the day, the transfer function gives you one clean equation that perfectly describes that input-output relationship for the entire system. Let's bring it back to our satellite. How would we find its transfer function? It's basically a three-step recipe. First, you use basic physics, like Newton's laws, to write down an equation for its motion. Second, you use that Laplace transform trick to simplify it. And third, you just divide the output, which is the satellite's angle, by the input, which is the force from its thrusters. Boom, there's your transfer function. And to visualize all this, engineers use something called block diagrams. They're like a super simple flowchart. You have your input signal, an arrow points to a box that represents your transfer function, and another arrow comes out with the output. Simple, clear, and powerful. But what happens if things go wrong? You know, if a gust of solar wind pushes our satellite off course? That's where the real genius comes in: feedback. You add a sensor that measures the actual output, and you feed that measurement back to the beginning to compare it with what you wanted. The difference between the two is your error, and the system's job is to make that error as small as possible. That's a closed-loop system, and it's the key to making things that can correct themselves. Now, that black box way of thinking is awesome, but it has its limits. For the really complex stuff, think multiple inputs and outputs all working at once, we need to peek inside. And that brings us to the modern way of doing things, the glass box approach, also known as state space. You can think of it like this. Control theory had a huge level-up moment right around the 1960s, thanks to the rise of digital computers. The old school, conventional theory was great for simple, single input, single output systems. But this new, modern theory, it was built to handle the tough stuff, multiple inputs, multiple outputs, and even systems whose rules change over time. And that's why we call it the glass box. We're not just looking at what goes in and what comes out anymore. With state space, the goal is to describe the complete internal condition of the system at any single moment in time. And that internal condition has a name, the state. The state is like a perfect snapshot. It's the absolute smallest list of variables you need, like position, velocity, temperature, to know everything important about the system right now. If you know the state, and you know the inputs from now on, you can predict the system's entire future perfectly. And this whole powerful idea is captured in just two incredibly elegant equations. Now, they might look a little intimidating, but the idea behind them is simple. The first one, the state equation, is the rulebook. It says, here's how the inside of the system changes from one moment to the next. The second one, the output equation, just says, and here's how the stuff we can actually measure on the outside is related to what's happening on the inside. That's it. This two-equation framework is just insanely powerful. It's the tool that lets engineers tackle those mind-bending problems, from coordinating all the motors in a complex robot arm to, yep, you guessed it, finally figuring out how to balance that inverted pendulum we started with. So we've gone from a sealed black box to a transparent glass box. And these aren't just cool ideas for a whiteboard. These are the tools that are quietly and invisibly building the world all around us. All right, let's pull it all together. What are the big things to remember? First, all control starts with a mathematical blueprint, a model that's always a dance between being simple and being accurate. Second, the classic black box method is awesome for understanding the simple relationship between what goes in and what comes out. But for the tough problems, you need the glass box state space approach, which gives you that complete snapshot of everything happening inside. You know, when you boil it all down, we've really been talking about two completely different philosophies. Two different ways of looking at a problem. Do you treat the world as a mystery box that you can only understand from the outside? Or do you try to build a transparent glass box so you can understand it from the inside out? These two ideas are what engineers use to build the automated world we live in. And that leaves us with one final big question. As our systems get crazier and more complex, from self-driving cars to AI-powered factories, the blueprints that got us here might not be enough. So the question is, what will the blueprints of tomorrow need to look like? What's the next secret language we'll have to learn?